All right, welcome everyone. Today we're going to talk about circuits. We're going to talk about Ohm's law and Kirchhoff's rules. This is a crash course in everything that you will need to know for the AP exam, so pay attention. The first thing we need to know when we talk about circuits is something called EMF. EMF used to be known as electromotive force, but it's understood as a different kind of quantity than a force. It's not really a force, but I think it's still a good way to think about it. EMF is what drives charge. So we've learned about charge when we think about what is actually pushing charge through a circuit, through a conductive material. This quantity we're going to call EMF. It's still called EMF, even though we understand that it's not necessarily a force. When you talk about the voltage of a battery, or you talk about the voltage of a power supply, what you really mean when you're saying that is the EMF. Okay, remember voltage, we talk about voltage as a potential difference. Voltage as a potential difference is different than the voltage of a source of EMF. They are very similar, but there is a distinct difference. The way that we measure EMF is energy per coulomb of charge. So that means we have joules per coulomb. So how much energy are we transmitting per coulomb? We move the same amount of charge, right? We can have the same current, which is a unit of moving charge, but we can transmit different energy. Okay, so in a circuit, again, EMF provides movement of charge through a conductive material. What we are going to see in a circuit diagram is something that looks like this, usually. Most of the time, we have this type of diagram where you have the long line as positive and the short line as negative. Okay, it will never be the long line as negative and the short line as positive. That does not happen. There are standards that everyone generally follows where you have the short line is negative and the long line is positive. This is the most used voltage symbol to my knowledge. Okay, the most used EMF symbol. Sometimes it will look like this. That is just a possibility. I will say that we are very much likely to see this version. Okay, the symbol of EMF is V in volts, and the standard that we are going to use is we are going to pretend that charge moves from positive to negative. So if we had a circuit loop here, we would say that the charge is moving in this direction. Okay, that's just the convention. We understand now that it is actually the electrons that move. So the electrons move from negative to positive. However, for drawing circuits, what we want is positive to negative. So that is the right way, right there. Okay, the most basic element in a circuit, other than the source of EMF, is a resistor. Resistors do literally what their name suggests. They resist the movement of charge that is quote-unquote pushed by the EMF source. And they dissipate energy from the EMF source as heat, normally. We are going to see the resistor symbol right here. If we are going to draw a circuit, we will see an example of this momentarily. We are going to draw a circuit. We are going to use this as a symbol for a resistor, this jagged line. The symbol for a resistor is R in ohms, O-H-M-S. Ohms. Okay. The symbol for an ohm is omega. I don't believe I actually wrote this down. So the symbol for an ohm is an omega. So we say we have 15 ohms is 15 ohms. Okay, omega. That's the symbol for it. Okay, current. Current is the flow of electric charge. It is I in amps, which we will represent as A. but the current is represented as I. There is no unit in a circuit that gives you current necessarily. Okay. How do we think about current, voltage, and resistance? I think that the best way to think about it, or if not the best, a very useful way to think about it, is water in a hose. Okay? The voltage of EMF is the strength of the water pump. Okay? That's the strength of the pump that is shoving this water through this hose. Okay? Resistance is going to be the size or the diameter of the hose. So how wide or skinny is it? And then current is the rate of flow of the water. Okay, so we have some water pump and it's pumping. So here's our, here's our pump. We have some hose that we are trying to deliver some water through, right? So the pump is pushing the water, Okay. If we have a much wider hose, right? We have a much wider hose, then we are going to be able to push a lot more water with the same pump, right? But we'll talk more about how that works in a second. Okay, so a very basic circuit. So this is using the uncommon, I would say, the less common version of an EMF source. But here is the EMF. The current, again, is moving away from the positive. Okay, so you can say it's moving in this direction. And here is a resistor. That's an example of what a resistor looks like in a circuit. Okay, so this black line here, this black line is simply a wire. And we are going to say that there is no resistance. We're going to say that there's no resistance in that wire. This is an idealized circuit, just like when we're dealing with Newton's laws, we're working in our frictionless vacuum. When we're doing our circuits, our very basic circuits, we are going to assume that we have a wire that gives us no resistance. In reality, this is not true, but it makes things a heck of a lot easier for us. All right, the very basic thing we need to know for circuits is called Ohm's law, and that is V equals I times R. V equals I times R. So what this means is that the EMF, or the voltage, is equal to the current, which is I, times the resistance. Oh, pardon me. My goodness. Apologies, I'm only human. Okay, so the electromotive force, the EMF, in volts, the voltage of the circuit is equal to the current that moves through the circuit multiplied by the resistance of the circuit. Okay, so if we know the other two, we can find any of the third, and it applies for all parts of a circuit. If we have multiple resistors or multiple circuit elements, this applies for all parts of a circuit, but we do have some rules that govern those circuits. And for the whole circuit, we must consider the total resistance, and we'll have to deal with some rules about that as well. All right, so series resistors. There is a rule for series resistors. They all receive the same current. They all receive the same current. If there is one thing that you need to remember, I'll say, okay, two major things. Series resistors receive the same current. We will see something similar for parallel resistors, but you need to remember that series resistors receive the same current. Okay, they all have the same flow of stuff going through them. Okay, the rate of transfer of charge, which is current, that is the rate of transfer of charge, must be equal at the beginning and the end of the circuit. Okay, we think about current. All right, let's draw our pretend water cycle again. Let's draw our pretend hose. And we'll try to make this analogy here. All right, so say that we have 1, 2, 3, 4, 5. Okay, there's 5 water molecules. Let's say they are moving, so we have 5 molecules in 1 second. So 5 molecules in 1 second. Okay, we have 5 molecules in 1 second moving through this spot right here. So we have 1 second goes by, and now there's 1, 2, 3, 4, 5 have moved through. And now they're gone. All right. That means that when we go over here, we still must have 5 molecules per second. Okay, so after another second, 1, 2, 3, 4, 5. Now let's imagine that we tighten up our hose here. So we put some sort of blockage. So now we have a smaller hose right here. Okay, now we have a smaller portion right here. We cannot change the amount of water that flows through there per second. That would create a backup. If there are 5 molecules per second moving through this spot and 5 molecules moving through this spot, if there are less molecules moving through this spot, then that's going to create a backlog, right? So we're going to have a whole bunch of extra water molecules stuck down here, and that's going to create a problem, right? That cannot happen. There still has to be 5 molecules per second moving through this smaller hose. That still has to hold, right? And then when you expand back to this large one again, we still have 5 molecules per second, okay? So the same thing goes for a circuit. Okay, same thing goes for a circuit. If we start off with 5 amps, we start off with 5 amps moving in this direction, right? This is positive, this is negative. Okay, we're following from positive to negative. We start off with 5 amps. Right here, we still have 5 amps. That means the same amount of charge is moving through this spot and this spot. Makes sense? We have the same number of electrons, right? Charge is measured in electrons. We have a basic unit of charge. We can't have less than an electron. Right? We have a certain number of electrons that are moving through these 2 spots. After we hit this resistor, it's going to resist that flow, so some quantity is going to change. But when we get to this spot here, right, we get to this spot, it still has to be 5 amps. Once we go past this resistor, that's going to dissipate some energy. That resistor is going to turn some of that energy into heat, okay? But we are still going to have 5 amps. Again, we're going to go past this resistor. Some stuff is going to change, but we are going to end up out here with 5 amps, okay? So that means we have 5 amps of charge, and then we go through this wire, and then we're back here, okay? So that means at any point in a series circuit, we have to have the same current. We have to have the same amount of electrons coming out of the voltage source and going back into the voltage source. The current must remain constant. Okay. This results in, this is a result of Kirchhoff's voltage law. Okay. So the sum of voltage differences across all parts of a circuit must equal 0. So voltage will drop. So voltage being a potential difference, there will be a potential difference across each resistive element of a circuit, across each resistor. Okay, so we get different voltages. We have different potentials. Okay, so that means that the current across series resistors, if we're going to use Ohm's law, we have to find what's called the equivalent resistance. Okay, so we're going to see how Kirchhoff's voltage law connects to this in a second. But we have to find the equivalent resistance of series resistors. In order to do this, we very simply sum the resistance of each. The total must be higher than each individual resistor. So if we have a whole bunch of resistors in a circuit, the equivalent resistance is going to be higher than any individual resistor. So that's actually a sanity check. This would be a sanity check. So when you find your equivalent resistance, the total must be higher than any individual resistor in this circuit, okay? So usually what you have is a source of EMF with a known voltage. Usually you know what the EMF of the source is. If we want to find the current is often what's being asked for. We know the voltage, we know the resistance, we want the current. Basically, all we do is we take each of those resistors and we add them together. As many as we have, we just add them all together and we get a total resistance. So what we care about is the equivalent resistance. Okay, Ohm's law, V equals I times R. The total voltage is the total current multiplied by the total resistance. Okay. Let's figure this out. Let's find the equivalent resistance of the circuit, then find the current and voltage across each resistor. This is going to tie back into Kirchhoff's voltage law, which we will talk about. So we see that first off, we have a 12-volt EMF source. All right, we have 2 kilo ohm resistor here, 2 kilo ohm, 2 kilo ohm. Okay, so these are all the same resistor. And remember that this omega is ohms, okay, resistance. So first we want the equivalent resistance. So what we want is R total, and that is R1 plus R2 plus ... Rn. So all of them together. So for this case, we have R total equals, we're going to call this one R1. Here's R2 and here's R3. This will help us keep things straight. So we have R1 plus R2 plus R3. 2 kilo ohms plus 2 kilo ohms plus 2 kilo ohms. Okay. This gives us 6 kilo ohms. Great. So that's our R total. That's 6 kilo ohms. So now if we are going to use Ohm's law, we have the voltage that we know, that's over here. So we have V total equals I total times R total. Our total voltage is just what is given. 12 volts is the total current multiplied by R total, which we just found is 6 kilo ohms. Okay, so you've got 12 volts equals I total times 6 kilo ohms. That means that the total current, I is current, is 12 volts divided by 6 kilo ohms. So that gives us that I total is 2 times 10 to the negative third amps, right? because 6 kilo ohms is 6 times 10 to the third ohms. That means we divide by 10 to the third. We get 10 to the negative third amps. Great. And now, let's actually just set up a little table here. So we have R1, R2, and R3. And we are going to say that we have resistance, current, and voltage. So, each of these are 2 kilo ohms, 2 kilo ohms, 2 kilo ohms. All right. Now, what is the current across each of them? Well, if we remember this very, very important thing that I told you to remember, series resistors receive the same current across all of them. So that means we have here 3 series resistors. They must receive the same current, and that current is going to be the total current. So they are all going to have two times 10 to the negative 3 amps of current. Super. Now what we need to know is we need to know the voltage drop across each of them. So if this is going to be the potential difference, this is the voltage drop. So we're going to use V equals I times R for each of these individual ones. So that means the V drop is the current, 2 times 10 to the negative third, times the resistance, 2 kilo ohms. So that means the V drop is 4 volts, and this actually is the same for all of them. Okay. And that's interesting. That's interesting because this means that after each resistor, we drop 4 volts worth of potential. Okay, we lose 4 volts worth of electric potential. And this goes back to the voltage law. So the sum of the voltage differences across all parts of a circuit must equal 0. Okay, so we have different voltage drops across each resistor. What's nice is that in this case, we have very similar resistors. Just draw this circuit again. All right. So here we have R1, R2, and R3. So we can see that the potential difference, okay, so the voltage drop right here is 4 volts, 4 volts, and 4 volts, right? So if we were to put a potentiometer from here to here, we would see that we have a drop of 4 volts. So we start off with 12, we drop by 4 volts, we drop by 4 volts, and we drop by 4. That gives us 0. Okay, so we start off with 12 volts of potential. Every time we go across a resistor, we lose that same amount of potential. So we end up with 0 at the end. We have 0 potential. We've lost, we've dropped all of our potential that we started with at the beginning of the circuit. Parallel resistors are different. Okay, this is the other super duper important thing that you must remember. Resistors in parallel must have the same voltage. So resistors in parallel have the same voltage. They have the same voltage drop across each of them. the same potential difference. Okay, so the same EMF pump, say that's like the water pump, the same source of EMF is pushing charge into all resistors equally. So you're not pushing more or less charge, right? You're pushing with the same, we're pushing with the same rate. But if the resistors are different, then the current, the amount of charge that is going through each will be different. A good example, if we're talking about the hose thing again, is if we start off with one hose here, and then we have a splitter. Okay, we have a splitter, and over here we have, let's say that's the difference between the two. Okay, here we have a very large, and here we have a very small. The same pump is pushing, right? But this, let's say, is a very low resistance resistor, right? It does not resist that water that much, okay? So the flow through this is going to be different than the flow through this, okay? We have the same push, but a different size hose, so the flow, the current, is going to be different. How do we determine this? Well, we need to know Kirchhoff's current law. So the current going into and out of a junction, right? A junction meaning, okay, this spot right here. So that we say is 3 or more wires, okay, 3 or more wires, right? We have 3 or more hoses here, let's say. Here's hose 1, here's hose 2, and here's hose 3, and they all meet in this spot. Similarly, here's wire 1, here's wire 2, here's wire 3. At this spot, they meet. Okay, so the current going into and coming out of this junction must be equal. That means we have the same amount of charge. Okay, this actually is a result of the conservation of charge. So if we have a certain amount of current going through into a junction, that means that that is a certain amount of charge. We cannot create or destroy charge. Therefore, however much charge goes into a junction per second, that same amount of charge must come out of that same junction per second. Okay? Same amount of current, same amount of charge. Okay? This means that different currents are going to go through each resistor, right? But the total amount of current must remain the same. And if it doesn't, that'll be a sanity check. Okay, that'll be a sanity check. If you add up the total current going into and coming out of the junction and it's not equal, then you know you made a mistake. Okay, so parallel resistors, again, what we have to do we have to start with our overall circuit. We have to start with our total circuit. We have to find the equivalent resistance of resistors in parallel. Okay, this will be your sanity check for parallel resistors. The total resistance is lower than any individual resistor. That's your sanity check. All right. If the total resistance is not lower than any individual resistor in the circuit, then you did something wrong. Okay. In order to find the equivalent resistance of the resistors in parallel, okay, when we need to know for our overall Ohm's law, which we have to do first for the equivalent circuit, the inverse, okay, be really careful with this. The inverse of the total resistance is equal to the sum of the inverses of the originals. So 1 over the resistor plus 1 over the other resistor equals 1 over the total. It does not equal the total, okay? I see this a lot. R total equals 1 over R1 plus 1 over R2, etc., etc. No, big no. That is not true. It is the inverse of the total resistance. All right, be careful. So let's find the equivalent resistance of this circuit and then find the current and the voltage across each resistor. All right, so let's first do our equivalent resistance. So these are in parallel, okay? So how do we know that they are in parallel? We have the same wire coming from our source connecting to multiple resistors, okay? This is how parallel circuits are often drawn. I think sometimes an easier way to think about them is like this. This circuit is the same circuit as the one I'm about to draw. These are the exact same circuit. That is the exact same circuit. So here you would have the 2 ohm, the 3 ohm, and the 4 ohm. These are exactly the same. You have one wire coming from the source and splitting into 3 branches. We have one wire coming from the source and splitting into 3 branches. Okay, just because this one is closer, or it seems closer to the voltage source, does not mean that it gets more current or voltage or whatever, right? Because again, let's remember, we are pretending that this has no resistance. We're pretending that this has no resistance. So all of the charge equally gets to all 3 of those, as it would in this. And of course, here we have a junction. So this one we have 4 wires. So the amount of charge, the amount of current, so the amount of current here must be the same as the amount of current in each of these. And that'll be our sanity check. All right, so let's erase this. And let's do it. Let's go for this. So we are going to find first the equivalent resistance, being careful that we say that 1 over R total is equal to 1 over R1 plus 1 over R2 plus 1 over R3. Okay, we call this R1, R2, and R3. So that means 1 over R total is 1 over 2 ohms plus 1 over 3 ohms plus 1 over 4 ohms. Okay? Now, can we just add these like this? No, we cannot. Absolutely not. Cannot just add them like that. Okay? If I see you add those up and you get, what, 2 plus 3, 5 plus 4 is 9. If I see you get 1/9, you make me sad. Okay, these have different denominators, which means we need to find an equivalent. So their lowest common denominator. Okay, their lowest common denominator in this case would be 12. So 1/2 is 6/12 plus 1/3 is 4/12 plus 1/4 is 3/12. Okay, now we can add them. Add the numerators. 6 plus 4 is 10, plus 3 is 13 over 12. Okay, what does this equal? 1 over our total. Okay, so we need to find the inverse of these. That means that our total is the inverse of this, which is 12/13. Okay. Now let's do our sanity check. 12/13. Is that less than 2 ohms? Yes. Is it less than 3 ohms? Yes. Is it less than 4 ohms? Yes, because it is actually less than 1. 12/13 is less than 1 ohm. We've done our sanity check, so we're okay. All right. That is our total resistance. Okay. So what do we know? We know that our total, okay, is 12/13 ohms. Okay. Now, let's look up at our voltage source, our EMF. It is not given, so what I will say is let's use just the general 12 volts. Let's use 12 volts. Just makes things a teeny tiny bit easier. All right. It's just very common to see that. So now we need Ohm's law. Voltage is current times resistance. Okay. So we have the total is the total current plus times the total resistance. Okay. So we have 12 volts is the total current times the equivalent resistance, which is 12/13. So that means that the total current is going to be 12 volts divided by 12/13, which is 12 volts over 1 times. So that is 13 amps. Okay, so we have 13 amps total as our total current. And this is going to help with our sanity check. All right. So let's list our overall quantities. Let's say our total is 12/13 ohms. It's a terrible omega. Our total EMF is 12 volts. And our total current is 13 amps. All right. So that's our sanity check for the total circuit. Let's move on to the individual circuit elements. Let's make a table. Okay, let's make a table. And we will fill it in. Oh, that's fine. Okay. All right, let's start with the resistance of each of these. R1 is 2 ohms. R2 is 3 ohms. And R3 is 4 ohms. All right. Let's say we want the current and we also want the voltage. We want the voltage drop. Okay. So what is the key to this piece here? The key to this is resistors in parallel must have the same voltage drop. Okay, must have the same voltage. That means that for all 3 of these resistors, they have the same potential difference across each of them. So if we treat it as one total circuit, something I forgot to mention. Once we find the total resistance, okay, we can draw this circuit like this. Okay, we can draw the circuit like this. So here we have 12 volts, and this total resistance, we can pretend that this here is a resistor that has 12/13 ohms, okay? So we can take all of these and we can kind of shove them all together into this one quote-unquote equivalent resistor. And the voltage drop across that equivalent resistor has to be the voltage drop across each of them individually. So the total voltage drop that we get has to be the total voltage, because we only have one equivalent resistor. So that means that the voltage drop across each of them is going to be 12. They each have a voltage drop, a potential difference, same thing, of 12 volts. So now let's start with R1, resistor 1. Let's find the current across it. So resistor 1, we have the voltage is the current 1 times R1, which is 2 ohms. That means that the current across this one is 6 amps. Okay. Resistor 2, 12 volts equals current 2 times 3 ohms. Okay. This means that I2 is 4 amps. And R3, 12 volts equals I3 times 4 ohms. That means that current 3 is 3 amps. All right, now sanity check, okay? Kirchhoff's current law. The current going into and out of a junction must be equal. Let's go back, okay? How much current do we have going into this junction? Okay, a total of 13 amps. We have coming into here, we have 13 amps. Yes, it splits between all of these, okay, but the total current must be the same. So we have the I total equals 6 amps plus 4 amps plus 3 amps. That gives us 13 amps. Sanity check. We're good, okay? So each of these branches is receiving a different amount of current, but due to conservation of charge, right? Current is just movement of charge, okay? The amount of current that we have going into all of these branches and coming out of all of these branches must be the same. We can't lose any electrons during all of this nonsense that's happening inside this circuit, right? Because current represents movement of electrons. We can't lose any electrons, okay? They all have to come in and they all have to come out. Okay, the last thing we need to know is very simple. It is power. Power is the amount of energy transferred per unit time. We've looked at this before with conservation of energy. It's in watts, joules per second. And there is a very simple formula for circuits. It is the current times the voltage, right? The current multiplied by the potential drop across that particular resistor. The amount of current multiplied by the potential drop. So the amount of power that any circuit uses can be calculated this way. Okay? So for any individual resistor, we can use the current through that resistor multiplied by the potential difference across that resistor to find the power. All right, so I'm going to stop this video here. I'm going to make another video specifically with just this problem, right? This is the highest level of problem that you will see on the AP exam. It is a combination of series and parallel resistors, right? So I'm going to stop this here, and then the next one is going to be me solving this problem. This is the most complicated side of the problem. If you want to, pause it right here, try this out, you want to find the voltage and the current across each of these individual resistors and find the power dissipated by those resistors. Be my guest, and then you can check the next video for the solution. Thanks.